I'm Mark Arenes, and this is Euler's Melting Pot. In this challenge, we try to complete every Project Euler problem in a different programming language. Today's challenge is problem number 3. Find the largest prime factor of 600,851,475,143. First, let's talk about primality. Prime number is an integer greater than 1 whose only divisors are 1 and its set. 2 is a prime number because its only divisors are 1 and 2. 3 is a prime number because its only divisors are 1 and 3. 4 is not a prime number because its divisors are 1, 2, and 4. 5 is prime, 6 has 2 and 3 as non-trivial divisors, 7 is prime, and so on. The first several prime numbers are 2, 3, 5, 7, and 11. It's a basic exercise in number theory to show that prime numbers are the building blocks of all numbers. Specifically, every positive integer is a product of prime numbers, and this product is unique. This is called the fundamental theorem of arithmetic. So, for example, the number 12 is not prime, because it has non-trivial factors 2, 3, 4, and 6. But we can write it as a product of prime numbers. Namely, 12 is 2 times 2 times 3. And anytime we write 12 as the product of some prime numbers, it will always be the product of 3 numbers, and those 3 numbers will always be 2, 2, and 3 in some order. So, we could also write this, or this, but we can never write 12 as the product of 4 prime numbers, or as the product of 7 and some other prime numbers. It's always these 3 specific numbers. So, it's meaningful to ask, given a number like this one, what is its unique prime factorization? And in particular, for this problem statement, we want to know what the largest prime that appears in its factorization is. Equivalently, what is the largest prime number that divides evenly into this number? Enough theory. Let's write some code. We'll use C++ today. First, let's write a function that takes a number and determines if it's prime or not. We'll use the long data type, which can store numbers up to 2 to the power 63, or about 9 quintillion. First, if the number is less than 2, we return false, because numbers less than 2 are not eligible for primality. It's not that they're not prime, it's that the question, is 1 a prime number, isn't even meaningful. For those interested, that's because 1 is what we would call a unit in ring theory, and only non-units are eligible to be considered prime. But intro to ring theory can be another video sometime. For now, it suffices to accept that 1 is not a prime number. Now, to determine if a number x is prime, we want to check every number from 2 up to x minus 1. If any of them divide evenly into x, then x is not prime, and we can return false. Otherwise, if we get to the end of our loop and we haven't found a divisor, we can return true. To check if a value divides x, we use the modulo operator. We've touched on this before, but as a recap, the modulo, or remainder of two numbers, indicated by a % sign in C++, is the amount that's left over when you attempt to divide the two numbers. In our case, the variable I divides into the variable x evenly if there's no remainder left over after division. So we want to check whether the modulo is 0. Great! We have a basic primality checker, and we can use it to generate a list of some small prime numbers. At a glance, this looks reasonable, but we can actually make it a bit more efficient. When we're looking for factors of a number, we don't need to go all the way up to x minus 1. The biggest value that can possibly divide into x evenly is x divided by 2, because any number larger will exceed x and then some when multiplied by any number. So we can make our loop shorter. In fact, we can do one better. Factors of a number always come in pairs. 2 only goes into 12 because 6 does as well, and 2 times 6 is 12. Likewise, 3 only goes into 12 because 4 does as well, and 3 times 4 is 12. In particular, these pairs always multiply together to get the original number back. We only need one factor, not all of them, so we only need to search for the smaller of these pairs of factors. A little bit of arithmetic shows that the pairs will always be, in some sense of the word, centered around the square root. That is, given a pair of factors multiplying to get x, one of them will always be less than or equal to the square root of x, and the other will always be greater than or equal to the square root of x. Since we only need one factor, we can safely stop our search once we've exceeded the square root. Something like this. Now we've taken a loop that ran in big O of n and converted it to a loop that runs in big O of square root of n, which is a substantial improvement. And now we're just a hop, skip, and a jump away from the solution to the whole problem. We have a working and fairly efficient prime number checker. Let's write a new function that identifies the largest prime factor of a number. To find the largest prime factor, we start at the top. The biggest value we need to consider is the input number divided by 2, for the reasons mentioned before. Inside our loop, we check whether the number in question is prime and divides our input. If both are true, we return it. Since we're starting from the top, the first result we find is the largest one. If, for some reason, we hit the end of our loop, we'll throw an exception and call it a day. In our main function, we simply call the largest prime factor function on our input value and print out the result. This code is probably correct. I say probably because, to be quite honest, I ran this for several minutes and it was still churning away. This approach is not efficient enough. Let's go back to the drawing board. Every number can be written uniquely as a product of primes. So, one new thing we could try is this. Let's start at the bottom from 2. Every time we find a number that divides into our total number, we can remove it from our prime factorization by dividing it out. In this example, we see that 2 divides into 1638. So we divide it out and remove it from consideration. Now we have a smaller number that is 1638 without the 2 part. Now, we try the same thing with 3. We find that 3 divides into 819, so we'll divide that out too. Now, we actually find that 3 still divides into the number, so we can divide it out again. Now, we try the next prime number, 5. 5 doesn't divide into 91, so no action is required. The following prime is 7, which does, so we'll divide it out. Now we try the next prime number, 11. 11 doesn't divide into 13, so we move on. Finally, we get 13. 13 divides into 13, so let's divide it out. And there's nothing left. We've removed all of the prime factors. The last number we divided by was 13, so in this case, our answer is 13. It's worth noting that this approach could also be used to get a list of the prime factors of a number. In this case, we just wanted the biggest one, so we ignored all of the others. But we could just as easily have accumulated the primes into a list and returned that instead. Now, let's see it in C++. We start with a result value of -1. This is simply a sentinel value to detect if our code fails. Then, we start iterating from 2. Anytime we encounter a prime number which divides evenly into our input value, we divide it out. We might have to do this multiple times if a prime divides into our input multiple times. As we do so, anytime we divide by a number, we make a note of that number, so we can return the final divisor at the end. Finally, at the end, we do one sanity check to make sure we found a prime factor, and assuming we did, we return the biggest one. We can actually do one better. It turns out, we don't even have to do the isPrime check. Since we're iterating starting from 2 and going up, it's impossible to ever hit a non-prime number that divides into what we've got left. For instance, 4 will never divide our number in this loop, since, in any case where 4 would have divided it, 2 has already done so, and we've divided that factor out already. So we don't even need the isPrime function at all. Now we have a working program, and as it turns out, it produces a correct answer in under a second. As a brief sidebar, a moment ago, I mentioned that we can also use this to calculate all of the prime factors of a number, including multiplicity. Let's make a minor modification to allow that. Instead of returning a single prime, we accumulate all of the prime factors, possibly duplicating factors as necessary. The resulting vector will contain all of the prime factors in ascending order, including multiplicity. Then, in our main function, we get the full list as a vector, and then we get the final element of that vector. For those unfamiliar with C++, vector is C++'s term of a dynamically expanding contiguous array of elements. Sort of like array list in Java. It's a contiguous sequence of data, and we don't have to worry about resizing, since that's all done for us behind the scenes. Now we have a solution. It's time to talk about the real language of the week, J. J is a tacit array-oriented programming language. Let's take those terms in order and figure out what this means. Let's start with array-oriented. This is a concept a lot of people have probably used without even knowing it. If you've ever used NumPy in Python, or if you've ever dabbled in Julia or MATLAB or R, you've probably seen some of these concepts. An array-oriented programming language is one that allows broadcasting operations along arrays. Let's consider Python for a moment. In Python, if I want to add two numbers together, I use the plus sign. Now suppose we have two lists of equal length. Perhaps they're three-dimensional vectors, or perhaps they're indexed over some problem space we're working with. And suppose we want to add each corresponding term of the lists to produce a new list. So we want a function addLists such that this is true. So the first element of each list gets added together, hence 1 plus 10 equals 11. The second elements likewise produce 2 plus 20 equals 22. And finally, 3 plus 30 equals 33. We might do that in Python like this. Loop over the indices of the two arrays, adding them together and concatenating the results into a new list. This is fairly wordy, but we can shorten it a bit using some of Python's sequence functions. Zip takes two lists and pairs them element-wise. Then we use a list comprehension to sum the elements of each pair. In some fields, such as scientific applications or game development, it's fairly common to need to perform these sorts of operations, either element-wise across two lists, or doing something combining each element of one list with some constant. For example, doubling each element of a list or adding 1 to each element of a list. Array-oriented languages allow us to broadcast built-in operators automatically. So, to add the lists together element-wise in Julia, we simply use the plus sign, with a dot preceding it to indicate our intent to broadcast. We can also broadcast an individual element over an array, or an array over an individual element. This works with operators and even ordinary functions like square root. J takes this one step further. In J, we don't even opt into broadcasting. It automatically applies to all built-in operators. You'll notice several things here immediately. First, arrays are not written using brackets and commas. In J, a sequence of numbers juxtaposed together is an array. There's no need for any explicit delimiters. Second, dash colon is the operator in J most similar to the equal sign operator in Julia and Python. The equal sign itself in J is a broadcasting equality operator, which is not what we want. As we did in Julia, either side can be a single value and it still works out. However, if the two sides are of different lengths, we get an error. That covers the array-oriented side of things. J also prides itself on being a tacit programming language. A tacit programming language is one that provides powerful combinatorial operators for composing functions, in order to minimize the number of times you have to explicitly mention function arguments. This style of programming was pioneered by APL, a language from which J draws heavy inspiration. The closest analog outside of the relatively siloed APL ecosystem is point-free style in Haskell. As an example, let's write a function to find the arithmetic mean or average of a non-empty list of numbers in Haskell. Now, if we want to get rid of the argument, there are several higher-order functions we can use in Haskell to compose the sum, length, and division functions in the way we want. There are lots of techniques we use to move arguments around in a function, and some people even consider point-freeing Haskell functions to be a sort of sport. But that can be a video for another day. The end result is something like this. The exact technique we use to get here isn't necessarily important right now. What is important is that, although it's possible to write functions in Haskell in a tacit style, it often makes the code less readable. It may be less obvious to the average Haskell programmer what this function does than the first version we wrote. Now, let's try the same exercise in J. We want to average a non-empty list of numbers. To average numbers, we need to sum them, take their length, and then divide the two numbers. / is a special type of operator in J called an adverb. This means it's not an ordinary function. In particular, it takes a function and produces a new function. In functional languages, we would often call this a higher order function, but in J we call this particular shape of function an adverb. / takes a function and produces a function. So the two characters plus / form a valid function in J, built up of the / adverb applied to the plus sign function. As a side note, J likes to use linguistic terms to describe concepts. So a J programmer calls values, such as arrays, nouns. Likewise, a J programmer would call a function that produces a noun a verb. Finally, we call a verb monadic if it's applied to one argument, and dyadic if it's applied to two. Most verbs in J are overloaded so that they can be used both monadically and dyadically. For example, the plus sign serves as ordinary mathematical addition when used as a dyad, but it serves as the complex conjugate operator when used as a monad. Note that in J, all dyadic verbs look like mathematical operators, in that they take one argument on the left and one argument on the right, rather than taking a comma-separated list of arguments like in many languages. In fact, comma itself is an ordinary verb in J, not any sort of special syntax. Now, / takes a verb and inserts it between each element of the input list. Using the terminology of J, it takes a dyadic verb, in our case the plus sign, and converts it to a new monadic verb, which operates on arrays. So in our case, it creates a function which adds all of the elements of a list together. Getting the length of a list is done simply with the hash sign, called tally in J. Finally, the usual choice of a division operator in most programming languages, the /, is already being used as an adverb in J. So we divide two numbers with the % sign. To average our list, we would write something like this. All of this is very similar to the Haskell case. We sum the list, and then divide by the length. But a tacit language has a big emphasis on composing functions. As it turns out, to get rid of the argument in this case, we simply write this. The +/% # sequence is called a train of verbs. Specifically, it's a train of 3 verbs: sum, divide, and tally. A train of three verbs is called a fork, and they compose in exactly the way that we want. The argument is given to the first and third verbs, and the two respective results are passed to the middle verb, which is treated as a dyad. So in J, the point-free version of our function is simply 4 characters plus /%#. That's a perfectly valid function. We can assign it to a variable and then call it later. Now, you might think that we're going to explore how to write our all prime factors function in J. You might think the next several minutes of this video are going to explain in detail how to write that function as a train of verbs that magically composes like our average function did. In fact, we can get sort of close with this. Prime factors is a function which produces the prime factors of a number, similar to our all prime factors function in C++, though the former doesn't account for multiplicity. I've used a few techniques here that we haven't talked about yet, namely the @ sign, which is used for function application, ampersand, which is used to partially apply a dyadic function, and quote, which is sort of like a for each loop. However, we don't actually have to do all of this. J comes with a fairly substantial collection of combinatorial and mathematical functions built in, and one of them does exactly what we want. The Q colon verb, when used with one argument, returns a list of all of the prime factors in ascending order and with multiplicity taken into consideration. So this, in C++, is written like this in J. Now, we've got some minor touch-ups to do. We've got a list of all the prime factors in ascending order, and we want the last one. The dyadic verb open brace takes an array on the right and an index on the left and returns the element at that position. That may be a little difficult for your brain to parse if you haven't used a language like this before. Curly braces and square brackets in J are not paired delimiters, so the open brace in this expression is simply a function like any other. Only the parentheses are actually paired together like they usually are. As with many verbs in J, open brace will broadcast over its left argument, so we can pass multiple indices and get each corresponding element out of the array. Finally, we can pass a negative argument to index from the back of the array, similar to the way indexing works in Python and Ruby. Negative numbers in J are written using a preceding underscore, not a minus sign. So this is -1. We want the last element of the array of prime factors of our huge number. So what we want is this. Take our large number, take all of the prime factors in ascending order, index the final element, and print it out. That's the entire program in J. This solves Project Euler problem number 3 in J. Tune in next time when we take on the 4th problem in a Windows batch file.